Welcome to the session on applications of forces, static particles. The objectives for this session are to find an unknown force when a system is in equilibrium. A rigid body or particle is in static equilibrium if it is at rest and the resultant force acting on the particle or rigid body is zero. Note that the particle is not accelerating, so A equals 0 and F equals ma equals 0. Let's take a look at the stages that we can use to solve problems in statics. We begin by drawing a diagram showing the forces acting on the particle. Then we resolve the forces into horizontal and vertical components on a horizontal plane, or resolve forces into components parallel and perpendicular to the plane if the particle is on an inclined plane. Next, we set the sum of the components in each direction equal to 0. And finally, solve the resulting equations to find the unknown forces, or force. Let's take a look at an example. Three forces act upon a particle as shown in the diagram. Given that the particle is in equilibrium, calculate the magnitude of the forces P and Q. Let's take a look at the first method for solving this. We're going to resolve horizontally first. We have 130 cos 45 degrees equals Q cos 60 degrees. And plugging in the values for cos 45 and cos 60 gives us 130 times 1 over root 2 equals Q times 1 over 2. And therefore Q equals 130 root 2. We can now resolve vertically, so 130 sine 45 degrees plus Q sine 60 degrees, and notice both of these forces are acting in the upwards direction, equals P, and this is acting downwards. So we can now plug in the various values for sine 45, for Q, and for sine 60. So we have sine 45 degrees here, and sine 60 degrees here, and we have this equation. Now we can plug in the value for Q, as shown, and then tidy up to give this expression for P. Now let's take a look at the second method for finding the values of P and Q. This method can only be used if the particle is in equilibrium. If the resultant force is not zero, the vector diagram will not be a closed triangle. Let's now convert this diagram of forces into a closed triangle. So here's our force Q, or Q newtons. And this angle here is also 60 degrees. And this angle therefore is 30 degrees. we can now shift the 130 Newton force down as shown. And this angle here in the triangle is 45 degrees therefore. And the missing angle in this triangle is 105 degrees because of course all the angles in the triangle add up to 180 degrees. So here's our closed triangle. And we can now use the sine rule to help us find the values of P and Q. So 130 divided by sine 30 degrees equals Q over sine 45 degrees equals P over sine 105 degrees. And therefore we have Q equals 130 sine 45 degrees divided by sine 30 degrees. And if we plug in sine 45 degrees and the value for sine 30 degrees, we have this expression. And this implies that Q equals 130 root 2, which is what we obtained in method 1. We can similarly find the value of P. So rearranging 130 divided by sine 30 equals P over sine 105 gives us this expression for P. And we can plug in the value for sine 105 and the value for sine 30 and then tidy up to give us this value for P. So now we have our values for P and Q as shown. When solving problems which involve inclined planes, it is generally easier to resolve parallel to and at right angles to the plane. So if this is our inclined plane, inclined at an angle alpha, and this is our mass m, or particle, this is our reactionary force and the weight mg. So let's take a look at some notation. R with a downward arrow, sloping downward arrow, means we're resolving down the slope, as shown. R with two vertical lines means we're resolving parallel to the slope. R with a diagonal upward arrow means we're resolving up the slope. And R with two vertical lines, as we mentioned earlier, means we're resolving parallel to the slope. Similarly, if we have an arrow, diagonal this time, but perpendicular direction to the slope, it means we're resolving perpendicular to the slope. And similarly, the perpendicular symbol also means the same thing. Let's now take a look at an example. Three forces act upon a particle as shown in the diagram. Given that the particle is in equilibrium, find the magnitude of the force P and the size of the angle alpha. So let's solve this. Resolving parallel to the slope using the upward direction as positive, we have P cos alpha minus 9 minus 8 sine 30 degrees equals 0. And this implies, if we rearrange this equation and plug in the value of sine 30, that P cos alpha equals 9 plus 8 times a half, which equals 13. Let's do likewise for resolving the forces perpendicular to the slope. So we have P sine alpha plus 5 minus 8 cos 30 degrees equals 0, since of course the particle is in equilibrium. And rearranging this and plugging in the value for cos 30 as shown gives us P sine alpha equals 8 times root 3 over 2 minus 5, which equals 4 root 3 minus 5. And so we have a value for P sine alpha and a value for P cos alpha. And hopefully you'll be able to spot that if we divide one by the other, we obtain tan alpha. So let's label each of these equations as shown and divide P sine alpha by P cos alpha. So here's P sine alpha and here's P cos alpha. Plugging these values into our calculator should give us 0.148323. So this is the value of tan alpha, and it implies that alpha equals 8.43677 and so on. If we now substitute this value of alpha in the first equation, as shown, we can find the value of P, which is 13.1 newtons. Now that we have found our value of P, we can round our value of alpha, as we no longer need that level of accuracy. So alpha equals 8.4 degrees. This brings us to the end of this session. If you have understood its contents, you should be able to find an unknown force when a system is in equilibrium. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.